Alright, so in this video I'm going to be explaining this important paper with the title Unsupervised Multiple Kernel Learning for Graphs via Ordinality Preservation. This iClear paper in 2025. Learning effective graph similarities is crucial for tasks like clustering, yet selecting the optimal kernel to evaluate such similarities in unsupervised setting remains a major challenge. Despite the development of various graph kernels, determining the most appropriate one for a specific task is particularly difficult in the absence of labeled data. Existing methods often struggle to handle the complex structure of graph data and rely on heuristic approaches that fail to adequately capture the global relationships between graphs. To overcome these limitations, they propose in their paper unsupervised multiple kernel learning for graphs, a model that combines multiple graph kernels without requiring labels or predefined local neighbors. Our approach preserves the topology of the data by maintaining ordinal relationships among graphs. You see, this is very important. If we can have ordinal relationships among graphs through a probability simplex, then allowing for a unified and adaptive kernel learning process. Is it possible to ensemble individual graph kernels and perform well in unsupervised setting? If so, then we can achieve better performance in graph-level tasks by learning the optimal kernel values in a data-driven manner. So an intuitive solution is to learn an optimal kernel from multiple graph kernels. You see an overview of the UMKLG model. The model starts with n input graphs which are processed through n multiple graph kernels with configurable hyperparameters. The learnable kernel weights combine the kernels into an optimal composite kernel because we have m different kernels between the two graphs. So it becomes this complex, multiple kernels. So we call it composite kernel, while preserving the ordinal relationship between the graphs. This ordinal relationship, you see that I and j, graph I and j, the kernel between graph I and j is greater than I and r, for example. Each of them is a graph, so the kernel between I and r is greater. So each graph is present. This is iClear 2025, right? 2025. I don't know why I think I have seen this paper before, even before 2025. So here, the learnable kernel weights W combine the kernels into an optimal composite while preserving the ordinal relationship between graphs. Each graph is represented as a point on the simplex, where Q is the initial probability distribution of graph similarities, and P is the power distribution that emphasizes stronger relationships. The goal is to adjust the positions of these points in the simplex to preserve both local and global graph structures inferred from K tilde. So as I said, you can just write as a sum of different kernels. You call this composite kernel. And from topology, you know about simplex. And here we are talking about probability simplex. So we preserve the topology between graphs by maintaining the order of similarity between graphs. We focus on the ordinal relationship according to learned composite kernel. Graph G sub I is more similar to graph 2G sub J than to graph R for any triplet. So for any triplet, graph I, graph J, graph R, we can find such. And we can have these ordinal relationships. Now, to define a feasible probability simplex, we consider a probability space over the set of graphs. The sample space is a set of all ordered pairs of graphs. The sigma algebra represents the events over the graph pairs, and the probability measure P assigns probabilities to each pair based on its graph kernel. So from this graph kernel, it's interesting that if you normalize it over all graphs, then look, we have got a probability distribution. The event of selecting this graph G sub J is denoted as GI/GJ. So given the probability measure above, each graph could be represented as a point in probability simplex, where G sub I is associated with the point Q sub I. This representation preserves ordinal relationships. Powered kernels. To effectively preserve the ordinal relationship, we capture key neighborhood structures by amplifying the stronger similarities between graphs toward a set of target probabilities. So fix just one I want to say among all different graphs like J, R, R prime, what. So what do I mean by probability? If this probability, if the similarity between I and J is higher than all the rest of them, then I is more similar to J, and that probability is higher. If you pick one graph among several graphs, then the one that has higher K has highest probability. So think about it as a selection mechanism. Now, let K tilde represent kernel values. If the ordinal relationship holds, then for any power, the corresponding probabilities in the power kernel distribution satisfies this. So it's straightforward. The entropy of powered kernel distribution is strictly less than the entropy of the original. So they move to the entropy. The idea is the same. Now, to preserve the topological structure during the learning of the weights W, we employ the Kullback-Leibler divergence. This KL divergence, we use it to see the similarities of these two distributions. The divergence quantifies the difference between two probability distributions, enabling us to align the learned distribution with the underlying graph relationships with minimizing the distortion of ordinal relationships. So it measures how much information is lost when P is used to approximate Q. This formulation includes a negative entropy, which plays a crucial role in regularizing the learned distribution Q. So the entropy term penalizes higher concentrated distributions and encourages Q to spread its probability mass more evenly across all graphs. So the reverse divergence tends to be more sensitive to cases where Q has a high probability and P assigns a low probability, thereby encouraging the learned distribution to avoid assigning high probabilities to regions not covered by P. So we have M graph kernels, initial weights, and the power hyperparameter. Our goal is to learn the optimal weights for combining the graph kernels. We don't know which weighted combination of the kernel is a good composite kernel, but this preservation of the this consistency of this ordinal relationship is the paradigm of this paper. Now, as I said, the goal is finding which W is good, so we are learning these weights, but we know what is reference Q and reference and target P. And of course, we have a set of unlabeled graphs. Typically, in this graph kernel learning and finding filters in a graph, like the method of Professor Michael Bronstein, they are supervised learning. But here, they are doing an unsupervised learning, because they are just making sure P and Q, this Kullback divergence between Q and P, just preserving this, preserving the order, and then here they are projecting this into unit simplex. So as I said, they normalize it to create a distribution. And for each graph G sub I, they do it. So I is just an index of a graph. They compare it. Because they have the reference Q and the target P, then we can project W onto unit simplex. Because this W can be anything. But now here we project it onto unit simplex by assigning the threshold to the first lambda that satisfies this condition, and we finally use the last lambda the algorithm finds. Here we adjust each element to a unit simplex. We find it where it is. That's it.